Okay, welcome to the Rotational Inertia Lab. In today's lab, we are going to determine rotational inertia of our moment of inertia, rather, of a few objects. And these objects are like this ring over here, or the disk over here, or something that it doesn't have the shape that we want. This is like a cross. And how to use experiment to directly determine the moment of inertia of these objects. So as we have discussed in our class is that moment of inertia basically determines how easy to rotate the object in a particular axis, right? So, and we say that if your axis, if the mass that makes the object is distributed further away from the axis, then its moment of inertia is high. If it is distributed closer to the rotation axis, then it would be low. Moment of inertia would be low. For example, if I simply take this pen, right, and it's very easy to rotate this pen this way, right? And the reason for it is that if you think about the rotational axis, it goes through the center line here, and when it is rotating, all the mass that makes up this pen, actually, they are very close to the rotational axis. On the other hand, if I rotate it like that, it's a little bit harder. And the reason it's a little bit harder is that now your axis goes perpendicularly to this rotational axis, and these masses are actually farther away from that point. And as an engineer or any other physical scientist, you have to figure out moment of inertia of an object, like you are making a propeller for a plane, and how easy it is to rotate that object. Again, just to show you this example, let's say that I have a disk and I have a ring, and if the weight of both or the mass of both of them are the same, then the moment of inertia of this guy would be lower compared to moment of inertia of this one. And if I want to, actually, if I let these guys go down on an incline, what would happen is that this this object will actually go farther, go faster initially at least, because it is easy to rotate this thing. All right, so a couple of things. First of all, moment of inertia. We said the moment of inertia, we are going to designate it with the letter I. And also the definition of it is basically mass times r square, mr square, where I goes from 1 to n, where n can be the number of particles that make up an object. So what happens here is that I have an arbitrary object, and I'm going to rotate it around a particular axis. So it is rotating with the angular velocity omega. And let's say that I have this object is made out of billions, trillions of particles, of course. So this n can go to that billions and trillions, whatever that number of particles are in that object. So let's say this is m1. The distance from the axis is r1. This is m2. The distance from the rotational axis is r2. This is m3. The distance from rotational axis is r3. So what you do is that to find, let's say there are only 3 points, okay? So to do this, all we have to do is it would be m1 r1 square plus m2 r2 square plus m3 r3 square. That would be really, if I break it up, if I have only 3 points that make up the object, then it would be that. But usually, of course, the object is made out of, as I said, the trillions and trillions of particles. So in the end, you just add up to mn rn square. Sorry, this would be square here. So that's the definition of moment of inertia. And as you can see that the moment of inertia will be high if you are, if the mass are further away from the axis. One of the things that we actually use moment of inertia in our daily life is actually when we walk. And when the babies start to learn walking initially, actually they automatically figure out how to distribute their mass as they're walking, otherwise they will fall down. So let's say that you are going to walk over a plank, right? Let's say on a very narrow plank over some, some river, some stream, whatever it is. And what you do is that automatically you extend your hands out, right, to keep your balance. Or let's say you are a tightrope walker, and what the tightrope walkers do is that they have a very long rod, right, or balance beam, and they hold that onto it. And the reason for that is to increase their moment of inertia, because if your moment of inertia is high, you're not going to rotate that fast. It'll be difficult for anything to make this thing rotate. So when you do this, you're not going to fall off very easily, because then the axis of rotation goes right through your body. And when you extend the hands out, what you do is that you're taking the mass which is closer to your rotational axis and taking it out there. You are preventing your body from rotating easily, right? So in today's lab, what we're going to do is we're going to measure this moment of inertia of these guys. A couple of things I should also remind you is that if I have a linear kinetic energy, by that I mean we write this Ke, let's say Ke linear, and we know this is half mv square, mass times velocity square. We know that by this time very well. We also have a rotational kinetic energy. And rotational kinetic energy, so let me write this down fully. Rotational kinetic energy so I'll just have rotational. It'll be half I omega squared. See the similarity? Both has half in front, and instead of m, we write I. What is I? I is my moment of inertia. It almost plays the role of mass when you rotate an object. And instead of v, I have omega, which is omega is the rotational motion, in this case, of course, angular velocity or angular frequency. And you know the relationship between omega and v, because v equals to omega r, where r is the distance from the axis of rotation to that point. So for example, when I look at this object right here and rotating, this r1 is smaller than r2. So if I look at that equation, I can see right away that the linear velocity of r2 or mass 2 will be higher than linear velocity of m1, because r2 is farther than r1. So when I multiply with the bigger r, I'll get a bigger velocity. You can think of the long playing record, for example. You guys haven't seen a long playing record, okay? Some of you have, and some of you haven't. So anyway, as the record goes around, the linear velocity of the points which is closer to the axis of rotation is smaller than the one that is further away, because it has to make a bigger circle. All right, so that's the preliminary thing, and we covered most of it in our lecture. So let's go through principle of conservation of energy, from which we are going to determine the moment of inertia. So remember that in our class, what I define it as, I call it PCOE. And what's PCOE? PCOE is the principle of conservation of energy. So in this case, of course, the energy is conserved in our experiment. What we are going to do is that we have a weight, a mass, and the mass is going to be connected to a rotational device. Okay? So, and what we're going to do is that we're going to let go the mass, and it's going to fall, right? Why is it falling? Well, because it has some potential energy. What is the potential energy? It's mgh. What is h in this case? H is simply the height or the distance of this object from the ground. M is its mass, and g is acceleration due to gravity. So what's my money in the bank is this, and where I'm going to spend the money? I'm going to spend the money in rotating this object. Okay? So in addition to it, I will gain some kinetic energy because this will go down and it will gain some velocity. It will be half mv square. And then rest of the energy will go into rotating this object, which is half I omega square. So my experiment kind of looks like this a little bit. Okay? And what I have is that I have this weight. So this is my table. So you can think of this as the H. So what's the potential energy? It's mgh. So my initial energy will be equal to my final energy. What's my initial energy? My initial energy is simply what's stored in this guy. And it has m. So I have mgh, which is the potential energy. As it goes down, before it hits the ground or whatever that is, it has now a velocity of half mv square. So this mgh goes into half mv square, which is the kinetic energy of this guy, okay, just before it hits the ground. Now, just before it hits the ground, what is its potential energy? Its potential energy is 0, because h is now 0. So we don't worry about its potential energy. So all its potential energy got converted into the kinetic energy of this guy. In addition to it, some of the energy goes into rotating that object. So what I have here is half I omega square. This object, this red object here, has only rotational kinetic energy. It doesn't have any half mv square because it's not moving linearly, right? On the other hand, this guy doesn't have any rotational energy because it's not rotating. Just to give you an example, when you are biking, as you're biking, let's look at the wheel of your bike. In that case, you have both of those terms will be there because the wheel is going forward half mv square and it's also rotating, which is half I omega square. In this case, these two energies are distributed. Half mv square goes here, half I omega square goes there. And all we have to do now is actually solve this equation to find I, okay? We also have to use V equals omega R, all right? Now, let's think about this a little bit, how we can do this. First of all, the way you actually solve any equation is to isolate what you're looking at first, which is I, right? So let me just look at this. What I can do is that I can say half I omega square equals mgh minus half mv square. So what I did is that because I want that guy right here, so I take it to the left-hand side and then I switch sides. So I got that. Very good. I am after I, remember this. So that brings me I omega square equals 2 mgh minus mv square, right? Then I isolate I completely. Anytime you want to solve anything, just isolate the term that you want. So 2 mgh over omega square minus mv square over omega square. All right. So that's your first step. And then you say, well, I don't know what omega is. Now, remember that the omega has a relationship with linear velocity, v equals omega r. V equals omega r. What's that v are we talking about? Well, that v is what this guy is doing. Now remember that this v is variable. As this mass goes down, its velocity increases, right? But this v is also, we can get it over here. I'll show you later on that what v I'm talking about. It's the base where the string is wound around. And as the string comes out of it, the string gains velocity because they are all connected. So as the object goes down, this string also gains velocity. So that v is actually, if you look from the top, if I look down, that string comes out, and this right here is basically your r, and this velocity is omega r, and the omega is basically how the angular velocity of this guy over here. So what I'm going to do is that I'm going to plug in this v equals omega r. That means that I'm going to change omega into v. So omega equals v over r. R is known, by the way. So what we're going to do, we're going to do 2mgh omega square. Now look what I will skip one step. I will write v square over r square, but I'll write v square on the bottom, and I'll bring r square on the top, because when you write v square over r square flips to the top. So that goes there, minus m v square on the bottom, right? And then I have a v square on the top, and I'll put r square on the top. I hope you can follow it. I skipped one step. So because I wrote v square over r square went to the top, it gives me just v square on the bottom. Okay? So that's easy. So then, let's see if this pen works. Let me just keep it as it is. 2mgh r square over v square minus mr square. This is all equal to I, by the way. One thing I also do is that, see this arrow sign? It basically says that it follows from that equation to that equation or that equation. Okay, it's good to have that, and that way you separate out the equations. Okay. So let's look at that. What's unknown over here? Well, the mass, I know that mass. This is the mass of this guy here. This is my mass. I know exactly what that mass is. What's my r? My r is actually, I will show you later on what my r exactly is. That's basically the base, the radius of the base. I know g is 9.8. I know the height also. How do I know the height? I have measured it at the very beginning over here, that height. What's unknown here? The unknown here is v. V is the final velocity of this mass. As it goes down, it increases velocity. What do you have to do? Well, this is what you have to do. As you release the object, you have a stopwatch. This time, the object goes very slowly down, actually. And you will have enough time to use that stopwatch. There will be not bias. It will be fine, actually. It takes a lot of time to get down there. So you're going to use a stopwatch to measure the time it takes for the object to go down. So the question is, so it goes down to height h, and you know the time. You start here and you stop here, you know the time. But what is the relationship between that? Is the velocity v equals h over t? Not at all. That means v is not equal to h over t, distance over time. Why that is not correct? Because your velocity is actually increasing, right? It starts at 0 velocity and goes up to high velocity, you have acceleration. You simply cannot use h over t. Let me see if I can use kinematic equation to get the right relationship. So I know the height, I know the time. What is my final velocity? That's my question. What's my final velocity, which is simply v? This v is my final velocity. What is that? Well, let me use some kinematic equations. One of the kinematic equations is v final equals vi plus at. What's my vi? My vi is 0 because the object started at rest, from rest. What's my a? I don't know what the acceleration is. It's connected to a string, and I have no idea. Acceleration is not 9.8, by the way, because it's connected to a string, connected to a bigger object at the top. I know my t. Where did I get my t from? I got my t from the stopwatch. I got my t from the stopwatch. I don't know what a is, so I need to figure out from another equation to that to get rid of a. How do I get rid of a? Well, here is another equation I can use. I know h equals vit plus half at square. That's my second kinematic equation. I know h because I measured it. What's my initial velocity? 0. Get rid of that. Now I have two equations. Vf equals at, h equals half at square. What I can do is that I can take my a from here and plug it in here. So let's say what my a is. Would you agree that a is 2h over t square? Take a moment to see how that came about, okay? So 2, I take it over here, cross multiplication 2h and t square on the bottom. So a is 2h over t square. And then I substitute it in this first equation. So let me write substitute in equation 1. So let me write it out here so that you can actually see a little bit clearly. So remember, equation 1 is Vf equals At, and I substitute A is 2h over t square times t. So my answer is Vf equals V is 2h over t. Easy derivation. Usually what happens in the lab, I ask students to actually derive it for themselves. I give them some time, figure it out on your own, and only then we will do this on the board. Okay? All right. So now we go back. I'm going to erase this part here. Now we go back here to our equation, and we got the V part. So let's write this down. 2mgh r square. What's my V? My V square is 4h square over t square. I multiply it by itself or square it. So what do I get? I get 4h square over t square minus m r square. Okay. So this one goes to the top, h square. So I got mgh r square t square, right? mg. On the bottom, I get 2. 2 over 4 gives me 2. H squared gives me h, 2h. Anything else I should get? I think I'm okay over here. Minus mr square. Okay? So my final answer would be, I would try to write it over here a little bit so that you can see it. So let me erase it one more time over here. My final answer is I equals, remember that's I equals, see that mr square? I take mr square common. And if I take mr square common, I get gt square over 2h minus 1. So you will see this equation in the write-up. This is your equation for today's lab. You're going to use it. T you're going to get from the stopwatch. H is the height that you'll have. M is the object that is going to go down. And that's number 1, comes after 0, before 2. Okay, all right. So you got all of these here. And what I will do is that the next step would be actually to show you the exact experiment. And then I will also go over the write-up later on. Just to tell you beforehand in the procedure, what you have to do is you have to find out the moment of inertia of 3 things. One is this cross over here. And then we're going to put either the ring or the disk for the second experiment. And what will have to happen is that when I have the disk over here, ring over here, sorry, that's the ring, then when I measure the moment of inertia, I'm measuring moment of inertia of both objects together, the cross and the ring. To find out the moment of inertia of just the ring, then you have to subtract the first moment of inertia of the cross from the combined one. Make sense? So let's go over to the procedure now. Thank you. Okay, now we are in the lab part of it. We're going to do the procedure. So remember that I showed you this disk, and we need to, this is not for the first part of the lab, actually this is for the second part, but we're going to measure the mass right away and write this down. This is an interesting scale, and it's a magnetic scale actually, and it works more or less with torque. So what happens here is that we're going to put some weights over there. It says 2 kilo, even though it's not 2 kilo actually. Because of torque, it feels like it's 2 kilos. So I have had 4 kilos over here. I'm measuring the mass of the disk, and then I want to move some of this out here. So that's 4.6 kilos. That's right here is 4.5. That's 4.4. It's almost there, but not exactly. So let's go to 4.3. And then we're going to move this over here. So we have about close to I would say, if I put it at 4.39, and then I can actually move this all the way, 4. Okay, that's pretty good. So I have 4 kilogram here, 300 grams here, and then I have 90 grams here, and I have 15 grams here. So what I got is, so it would be this is 1,000 grams, so that's 900. So this is close to, let me see. I even have to look it up carefully, actually. So we got 4.3, and then we have a 0.9. So 4.3915. So the mass is 4.3915 kilogram. I'm going to more or less make it round. So I'll get it 4.4 kilogram, okay? So 4.4 kilogram, sorry, I should have made sure that this is my M disk. We're going to use it at the very end of the lab, but I'm just going to make that measurement and put this away. And the ring, I'll take, sorry, my apologies actually. This is the ring. This is the ring. And I'm looking at the disk. And this is the disk. Okay, so this one is let me take this out, everything back here. So I have 2 kilos over here, and I have another 1 kilo. So that's 1 kilo is too much. So let me put it back, and I would have this about, they're almost similar in mass, slightly different. So it's 700, okay, and then we're going to put this out here. That's good enough for me. So that's about 4 kilogram and 700 and about 220 kilograms. So it will be 4.72, but I will just keep it as 4.7 kilogram. Okay, so those are the two numbers. Keep that numbers in mind. Write this down somewhere, and I will show you later on when we'll do the write-up where these numbers will go. Okay, thank you. Okay, so now we are with the experiment, and we're going to drop that mass, and that mass is, I believe it's 100 grams, isn't it? So, and we have a predetermined height from where we're going to drop it, and we said it's about 82.5 centimeter, which is 0.825 meters. We're going to write this down on the board a little bit later on. And what we're going to do is to release this across, and because this is mgh, this mass it has the energy of mgh. This mass will fall through the height h, which is 82.5 centimeter, and as it goes down, it'll pick up speed, and this is going to rotate faster and faster. So, and Hawaida here is going to help me. She's going to give us the time t that is essential for our calculation, and we'll do it 3 times for this first experiment. Okay, so let's go. Okay, we're ready. So 1, 2, 3. All right. 2.12. I'm just going to write this down on the board so that we do 2.12. That's in seconds. Okay. We're going to come back and notice that this is table 1, and I wrote here I1. This I1 doesn't go with it. This is T1, 2.12 seconds. I1 means that we're going to measure the moment of inertia of the cross. That's the I1. Okay, so we will do 2 more time measurements, and then we will move on to the time measurement for the other, for the disk and the ring. Okay, so let's go 1, 2, 3. 2.26. That's good. Now, we're doing this, the time measurements, 3 time measurements, one after another. But in principle, when you're in the lab, what I expect students to do is that they take the first time and they do the calculation right away and find out the moment of inertia for the cross. The reason for that is you would know right away that whether you are on the right time or not, because the moment of inertia of this guy is really pretty small. It's on the order of 10 to the power minus 3 kilogram meter square, by the way. That's the unit for moment of inertia. So 10 to the power minus 3 is a few times 10 to the power minus 3, 0.001, 0.002, 0.003 of that order. So you should be on that. It's not 10, it's not 100, it's not 1 even, or it's not 0.1. So that gives you an idea that whether you are measuring your time correctly. Okay, let's go now for the third time. 1, 2, 3.
2.15.
Very good. So that finishes our first experiment. But when you look at the write-up, there's a lot of things you have to do before you can move on to the second experiment, because you have to find out not only the moment of inertia of this one, average moment of inertia, you have to also calculate the sigma or the standard deviation for your results. Okay, so there are a couple of other things I should actually mention before I move on. I should give you the mass of this thing. I'm going to write this down on the board, and I forgot to measure the radius r of this winding thing, or the base actually, and the base is only r is only 2.2 centimeter. 2.2 centimeter. I'm going to write that down on the board. I just want to mention this. The rotation is happening due to the base, and the base is only that big. Okay, you are going to ignore these wide side wings, and what happens that when the string actually rotates, this is the velocity it gets because it is wound around this base right here. So what I'm going to do is that I'm going to write down 2 things that over here. One is the mass that I need, and the mass is 100 grams. 100 grams is actually 0.1 kilogram, and then R, which is 2.2 centimeter. 2.2 centimeter is 0.022 meters. We need those 2 numbers for your calculation. So without any more talk, let me just, it could be either one of them. Just make sure that when you are in the lab, don't drop it on your feet, but you're not in the lab, so you're lucky. You don't have to worry about it right now. So this is one thing that I always warn my students about, is not to drop this on their feet. So what I have now is the disk with the cross. One thing I should tell you also, that if you have a symmetric geometric object, it's very easy to calculate this moment of inertia from analytical equations. But when you have something very odd, then you have a problem, and then you have to resort to an experiment like this. So even the cross is kind of symmetric. I can calculate its moment of inertia. But let's say you have something like this, and it has some odd extensions and stuff like that. So in that case, it is better, like I can put this up here and measure the rotation rate and things like that, and I can find out the moment of inertia of this object. But it depends on the axis, by the way. So when I put it like this, it means I'm going to find out moment of inertia on this axis. If I put it like that, then I'm going to find a moment of inertia on that axis. But then it gets complicated, of course, because as you see, that thing is not symmetric. So as I said, that the experimental version also gets complicated when you use different types of object. So anyway, so let me wind it around because it has this tendency to go inside it. So let me take this out, and I'm going to wind it. Okay, so what we have now is the disk plus the cross system. Disk plus the cross system, okay? So we're going to go with the same method on count of 3. Whether is going to start the stopwatch. And let's go. We have 1, 2, 3. Go! It didn't go anywhere. Well, my apologies. Let me see what's happening here. It's possible that I need to put some more mass on it, by the way. And let's see if it's entirely possible my mass will change. Let me see what happens now. It is moving, but let me put some mass and see how fast it moves. Well, it's all part of the experiment, okay? So if something doesn't work, you kind of change it, and then you do this. But I am getting stuck here somewhere. The question is why I'm getting stuck here. Okay.
I think it's catching.
It's catching. Let's see what happens now. I think this might work now. It's still catching. All right, let's figure this out for a second. Okay, so what happened is that our string was catching under the base over here. So we fixed that problem. We also, what we did is that we added another 200 grams to our original 100 grams. So right now we have 300 grams. So for your table 2, you have to take into account that this m, small m, is 300 grams, which is 0.3 kilogram. So, so we're all set with this setup. We have the cross, and we have the disk on top of the cross. We're going to measure the moment of inertia for this combined system. So we're going to take 3 times. So this is the first time. 1, 2, 3. So remember that we're going on table 2 here, and these are the times. So we go to T1 for this is 5.34 seconds. Okay?
And the mass changes.
And the mass has changed. Thank you for reminding me for that. For this table, my mass is 300 grams, which is 0.3 kilogram. My height hasn't changed. My height, I better write this down before we forget it. My height is 82.5 centimeter, which is 0.825 meters. This height will be also applicable for your first table. Okay? So we are ready to look at our second time. You keep careful here so that it is within the... The other thing about experiment you have to be careful about is that your string has to be parallel with the wheel over here, and they shouldn't be at an angle. Okay, we're all set. So we go 1, 2, 3.
.70.
Now the timings will be slightly different for each time because, as I said, the system is not perfectly smooth, and when it unwinds, it all depends on what it encounters over here. So this is a good principle of conservation of energy experiment because the energy, which is the potential energy of this guy, is being expressed as the rotational energy of this and the linear kinetic energy of this guy here. So we're ready for the very last time for this this experiment right here. 1, 2, 3. Okay, so the numbers are not way off. I think that it's not as tight as our first experiment, but you do expect much larger dispersion as the time goes on because there are a lot more uncertainties coming into in this type of as this falls, it catches on to the base and things like that. So, but still, it's okay.
Would it make any sense to do one more and then do 3 closer and
No,
roll out?
I think what happens here is that we do want to have, if there is a big deviation or dispersion, that's okay in a sense that that's part of the experiment because nothing is precise. So when we do the standard deviation, it actually shows up in our calculation. So, so this one is I2, but remember I2 itself is actually what we did was I1 plus the disk. So we have to subtract of I1 to get the disk. Sorry, this was I disk. Okay. Move on to I3. What I3 would be? I3 would be I1 plus the I ring. Okay. What I'm going to do is I'm going to take the disk off and replace it with the ring, and we'll do the same procedure. Hopefully I'll not have any catch here. I have to wind it properly. Okay, I think we're okay. We're ready to go. So count 1, 2, 3. All right. 7.29. Well,
on the mass of 300 grams.
yes. So the question is that are we expecting this time to be so different than this is the ring and that was the disk? And what happens here is that what we decided is that which one would have more moment of inertia? Well, we said this one should have more moment of inertia, even though it has a little bit less mass than the disk itself. So, so what happens that when you have more moment of inertia, it takes a long time to get it rotating, and that's what shows up in that time actually. So So we'll do 2 more. It almost feels like, like in half an hour is going by just before it drops, right? Okay, so we're ready to go. 1, 2, 3.
Sorry, I messed that up.
Oh, we missed it? Okay, no problem. So we'll do one more time.
Yeah. I got 6.65 and I know I stopped it before.
Okay, let's try one more time. Okay. 1, 2, 3.
6.87.
All right, 6.87. So we'll do the last one. Ready to go. Okay, this will be our last time measurement. 1, 2, 3. 7.75.
Started much slower this time.
Okay, well, I mean, it's okay. We are going to average this at some point of time. It's okay, but you can see the dispersion gets higher as the time gets higher. But this all related to moment of inertia of the disk, which is obviously higher than moment of inertia of the, moment of inertia of the ring, which is higher than moment of inertia of the disk itself. Okay, all right. So what we want to do right now is we have these numbers on the board. What I want to do is just say a couple of things before we go to the write-up. You have the equation to solve the moment of inertia. We derived it, remember? And the variables that go in there are the mass, m, small m, and the height, h. Then you also have the r. We'll go over to the other side of the board and we'll show you explicitly. The small r. And g, you are going to take g to be 9.8 meter per second square. And that's all you need to do. So let me just go to this side of the board. And for the very first table, you're going to use this mass, which is 0.1 kilogram. For the other two tables, you have to use the higher mass, okay? The r, you need that r. It is 0.022 meters, only 2.2 centimeter. It's actually very small. And height, again, let me write down the height for you one more time. Height is 0.825 meters. That's the height you need. And g, I said, will be 9.8 meter per second square. Okay, and that's all you need other than the time. What you're going to do is that you're going to calculate I1 for each one of these times. Remember, there is a time in our equation. So you're going to get I1 for each one of these. And then what you need to do is that you're going to take the average of these I1, average I1, and then you're going to calculate the sigma for this I1. By this time, you're very adept in finding sigma. You have already written a program, remember? Hopefully. So, and you can calculate that sigma for this I1. So that will be the first part. And for the second part, what you want to do is, again, you're going to get the I2s for this guy, and for this guy. And you're going to get an average I2. But then to get the ring, I have to go back and look at my write-up, whether I recommend doing each individual or maybe I recommend actually doing the average. So basically what happens that average of I2 minus average of I1 would actually give you the I of the disk, I of the disk. That makes sense? The I of the disk. Now, I also recommend doing the sigma for I2. So what you have is that you have sigma for I2 also. So now the question is, what is the sigma for I disk? Now pay attention to it. You got the error. Remember, sigma is standard deviation. You got the error for I1. You got the error for I2. But I2 has two things mixed in it. I2 has the moment of inertia of the cross and also moment of inertia of the, I kept looking at it, moment of inertia of the disk, which is this one, right? This is the second experiment we did. So the errors are now mixed together, you understand? Because when you are subtracting one from the other, this error is compounded with that error. So this sigma of the disk itself will be higher than sigma of these two together. So, and the formula that you're going to use, sigma of the disk is equal to square root of, this goes as kind of Pythagoras theorem, sigma 1, sigma I1 square, sigma I2 square. That will be your sigma disk. So when you write down your I disk, you have to write it down. Your I disk would be simply now I disk plus minus sigma disk. That will be your result with error. So it's a new thing that we're introducing right now. If you are going to subtract one from the other, and then your errors are going to go up also, and they go up like this. If you're dividing or multiplying, that's a little bit more complicated. That formula gets a little bit more complicated. We're not going to do that right now. We're simply doing subtraction. If you're adding up these two, you use the same formula, by the way. So that's for your I disk. Everything that we talked about here goes here, because instead of the disk, we're doing the ring. So again, you are going to take the average of I3 minus average of I1, and this would be sigma I1 and sigma I3. So everything would be the same as this table. I'm going to go over now to show you the write-up, and there is a conclusion. You have to do a few more things at home that you can do very easily, and we'll talk about that when I go over the tables in the write-up and the conclusion. Okay? Okay, so by this time you know how to get to the write-up. So I'm not going through the main page, and we'll start here with the moment of inertia lab write-up. And as you know that we described the objective of this, measuring moment of inertia of different objects. And this is the figure of the experiment that you just witnessed. And everything else here, the theory part, we went over with you on the board. We actually started from a PCOE, principle of conservation of energy, and wrote down the potential energy of the small mass on the left-hand side, and its kinetic energy, and also the rotational energy of the rotating object. We also derived the final velocity, turns out to be it's 2h over t. That's equation number 2. And then on the board, I showed you how to derive the last equation. It looks kind of complicated, that how you get from equation number 1 to equation number 3. You can go through this. And one more thing that you need is V equals omega r, which is also written over here. So that's the equation you're going to use. What are the unknowns here? The unknowns here are the mass that you're going to use. The r is the small radius. G is 9.8. T you're going to find out using our stopwatch, which we already did. And height is the height, h is the height through which the small object drops, right? So keep that in mind, that equation number 3 is what you're going to use. So, and then this is table 1. And even though I said use different mass for each trial, we're used only one mass. So in this case, mass was 100 grams or 0.1 kilogram. Remember to convert all your grams into kilograms and all your centimeters into meters, right? Kilogram and meter, those are our bread and butter. So then you got the three T values. We got it on the board. Hopefully you wrote it down, or just you can always back up the video and get those numbers again. And for each T, you get an I, and that was equation number 3, right? That's what you're going to use. Then once you got your 3 I1 values, you're going to average them out, and then you calculate the sigma for those 3 values. And then we put the disk on the cross, or you put the ring on the cross. I forget which way we actually did that in the video just before. But in any case, and you repeat what you did for table 1. And in this case, we changed the mass slightly. So the new mass is 0.3 kilogram. Our height hasn't changed, so keep the H same. Your R also is the same, okay? And then again, we gave you the 3 times. Just be careful that whether you're going to use the disk or the ring. So we did the disk for the second experiment, so everything is okay right here. And notice that I wrote down here how to get the disk, moment of inertia of the disk. It is average of I2 minus average of I1. And then also you get the sigma for the disk, which is root over sigma I1 squared plus sigma I2 squared. And that basically ends the moment of inertia for the disk. We repeat it for the ring. Again, I wrote here use a different mass for each trial, but we're okay with the same mass for this experiment. M will be 0.3 kilogram. Your H and R are the same. Those haven't changed. And again, those are the 3 times that we actually did the experiment. That was on the board. And you find out the average of this, and then the average of the ring would be simply I3 minus I1, and that ends that part of the experiment. The next parts are basically theoretical. What we have here is, if you notice on the cursor, the I disk, moment of inertia of I disk theoretical is big M R squared over 2. Now, what's the big M? Remember, at the very beginning of the lab, we measured big M with our big scale. And if this was the disk, I remember that the disk was about 4.7 kilogram or so. And the only other thing I have to give you, and I'm going to give you right now, remember this number, and we will try to write it down later on in the board, but you need that big R. So what is the big R? The big R is simply, I need to find out the big R, and I'm going to calculate that for you right now before we forget. So the big R is 12.5 centimeter. Remember that number, 12.5 centimeter, which is 0.125 meters, 0.125 meters. This is the radius of the disk itself. So right here, your M for the disk is 4.7 kilogram, and R is 0.125 meter. You have to square it, divide by 2, and you get the moment of inertia theoretical for the disk. What you're going to do is that you actually look at this number, and then you take the fractional difference between this theory and what you experimentally got, which is up here, I experiment, right here. And that's the fractional difference between that. All right, now same thing we're going to do with the ring, and I have to apologize here. Actually, I thought I fixed it, but I didn't. See that it's written I disk, it should be I ring, because I disk I did already here. And this should be I ring, and this I ring has an outer diameter or an outer radius and an inner radius. And I'm going to give you these numbers right now. Please write this down. So the outer diameter is 12.5 centimeter, and I'm going to give you an inner diameter soon. The inner diameter is 11.25 centimeter. So hopefully we can show that to you on a separate table later on if you don't remember it. But let me repeat it one more time. The outer diameter is 12.5 centimeter, which is 0.125 meters. And the inner diameter is 11.25 centimeter, or 0.1125 meters, right? 12.5 centimeter and 11.25 centimeter. And those are the two numbers. You have to put it in here in meters, by the way. And your M, we calculated, your M was 4.4 kilogram. Your M was 4.4 kilogram here. And you calculate this would be your theoretical value for I disk. And you again compare it with the experimental value that you determined from the experiment itself. And hopefully it's not a very large number. In the lab, what I do when we have like 8 groups or so, I have all of them to come up to the board and figure out which group has done the best actually with their experiment. So these fractional errors are the lowest for them. The way we end this lab is just to think about a couple of things. One of them was a common mistake is when we want to measure the R for equation 3. This R is basically not the radius of the disk or the ring that I just gave you, which is very large numbers, like 12.5 centimeter. But it's only a few centimeter, right? So this small r was only 2.2 centimeter. But what happens in the lab, if you're not careful, you want to take the big R. But remember that the string is wound around the base, and the base is very small, and that's all we care about, the base. So that's what I meant. Do you know exactly which R we have in mind? It's a small r we're talking about. 2, what does moment of inertia mean to you? Are you surprised that the values for moment of inertia of these objects are so low? The moment of inertia of these objects are really low. For the disk and the ring, you will find them on the order of 10 to the power minus 2 or 10 to the power minus 1 kilogram meter square. The unit of moment of inertia is kilogram meter square. Number 3, I want you to find out an approximate value for your moment of inertia. I'm talking about your moment of inertia, okay? That means your body's moment of inertia for an axis going through your center of gravity, but parallel to the length of your body. So the first one is like you're standing and rotating. So all you have to think about yourself as that your eye is like a solid cylinder. And if you're a solid cylinder, then the formula that you're going to use is actually this disk, mr squared over 2. Not that complicated formula, mr squared over 2. And you will find out that this moment of inertia will be bigger than for the moment of inertia of the disk and the ring that you found out in today's lab. Again, the first part is easy. Again, just think of you just standing and just rotating as you stand, okay? So the formula that you're going to use is mr squared over 2. You know your mass could be, let's say, 60 kilogram. And then what is the R you're going to take? The R you're going to take is from the center of your head to the extension of your shoulder. It could be, I would say on the order of, I'm measuring it as I'm speaking, let's say on the order of, let's say 25 centimeter or so, which is 0.25 centimeter, 0.25 meters. So it would be 60 kilogram times 0.25 square divided by 2, okay? So again, the unit will be kilogram meter square. What I want you to do, and this is a little bit tricky, compare this with an axis that is perpendicular to your body. It is like you are now a gymnast actually. So the gymnast is going around this rod. Okay, I don't expect you to do this performance, but this is the half of your body actually right here. So this is like a bar right here, and you're rotating around this thing. And what you have to do is a little bit complicated thing. which is m is actually your 60 kilogram, the same as your mass. In this case, r is the small r, which we decided was about 25 centimeter, 0.25, and L is the length of your body. So you measure the length of your body, it could be 160 centimeter, 170 centimeter, convert that into meter for sure, which would be 1.6 or 1.7 meters, and so on and so forth. I hope this makes sense. So this is your body, this is your head, this is your feet, and you're rotating around perpendicularly to that axis. It's a much harder to do than the first part. So this will be mr squared over 2, and this formula is that complicated formula, okay? Now, what you'll find out that this is much, much bigger than this one, because this is a much difficult thing to do. So your moment of inertia is much higher than that. Okay, so that ends today's lab. If you have any questions, hopefully I can answer that during our office hours or online by some other means. We are all discovering how to communicate properly through online. And I hope that you had fun with this experiment, as I had. Okay, I'll see you next time. Thank you.